Okay, we're going to take you into another topic in S1 called discrete random variables, otherwise known as DRVs. Okay, the burning question, what is a DRV? What is a discrete random variable? So the easiest way to describe it is this. It's a variable that represents the value obtained when we take a measurement from an experiment. So for instance, a discrete random variable could be the number of cars that pass in the road. It could be the number of shoes you own. The first thing I'm going to say about it is a DRV, or a discrete random variable, must be numerical. All right, number of cars, number of shoes. It cannot be anything that doesn't have a number in it. So it can't be the colour of shoes or the colour of car. It has to be numerical. The second thing I'm going to say about a DRV is we describe it using a capital letter. So for instance, I could say let X be the number of cars, or I could say let P equal the number of shoes. So it's always described in these capitals. Okay, these questions look awful, but they're actually really simple. Find the probability distribution for S, the score on a die. So here is the discrete random variable. It's a capital letter S, and it describes something numerical, the score on a die. 1, 2, 3, 4, 5, 6. Now when it says find the probability distribution, that sounds like it's going to be awful. It's actually really simple. It's just a table that holds together every single value the random variable could be. So 1, 2, 3, 4, 5, 6, and their associated probabilities. So it's just a table of probabilities. That's all it is. That's all I'm being asked for. So I'm going to get my table ready. So what do I know about this? I know that I can have 1, 2, 3, 4, 5, 6. Now, when I've decided that the discrete random variable is the score on a die, if I know one particular value that could be, I don't use a capital, I use a small case letter. So that's actually a small s. And then what I want to do is I'm going to introduce you to this notation, probability bracket big S equals small s. Now all that means is, if we read it, this just means the probability, all right? So that I want the probability that my capital S, which is here, the score on a die, is equal to one particular value. And I've put the particular values here. All right, there they are, 1, 2, 3, 4, 5, 6. So if I were to fill this one in here, I'm wanting the probability that the score on a die is equal to 3. Well, we can all do that, can't we? It's the 6th. All right, don't know why the box is. Let's take the box out. All right, so that's the 6th. And this is, I've chosen this example absolutely deliberately because there's nothing to do with it. All right, we know that the probability of all of these is a 6th, and that's it, done. That is the probability distribution for S, the score on a die. Now, if you notice that the probabilities are all the same, which this one is, it's called a uniform distribution. Okay, all right, so that one's got its own name. Okay, a more complicated example now. I'm going to throw a dice until I get a 6, or until I've thrown it 3 times. And I want to find the probability distribution. Now, the probability distribution is just a table of probabilities, so here it comes, for this random variable, capital T. So I want the probability that capital T, what is T? It's the number of throws equals one of the outcomes. Now, the outcomes, the small t, I don't know yet. There's a couple of things I can do to find out what these outcomes are. I can either do a sample space diagram, or I can do a tree diagram. And this question lends itself to a tree. So let's have a go at a tree. So I'm going to throw the dice. I'm either going to get a 6 or I'm not going to get a 6. And the probability is a 6th or 5/6. And if I get a 6, I stop. All right, so I've stopped here. This one here I didn't get a 6, so I throw again. I either get a 6 or not a 6, and that's a 6th, and that's 5/6. And if I get a 6, I stop. Or this one here, of course, if I don't get a 6, I go again. So a 6 or not a 6, so I'm going to get a 6th or 5/6. Now, if I get a 6, I stop. but also look carefully. If I throw it 3 times, I stop. So I stop here. Now, the question is not about getting a 6 or not a 6. The actual random variable is t, the number of throws. So what I'm interested in is, first of all, I would say to myself, have I thrown it no times? Well, of course I haven't. That's ridiculous. If I'd thrown it no times, nothing would have happened. I always check 0 kind of first. Then I'm thinking, have I thrown it 1 time? Well, if you think about it, that's here, isn't it, on the tree? 1 time was I threw it once and then I stopped. So the probability of that is a 6th. Okay, have I thrown it 2 times? Is 2 one of the outcomes? Right, in order to throw it twice, I would have come along this route, which means I would have done 5/6, because as the tree diagram we times along the stems, 5/6 times 1/6. And 5/6 times 1/6 is 5/36. Okay, have I thrown it 3 times? Now, be really careful. To throw it 3 times, I would have come along this route. So that's 5/6 times 5/6 times 1/6. Or I could have come across this route in order to throw it 3 times. 5/6 times 5/6 times 5/6. So I need to work out each of those individually and then add them together. Okay, so I think 5 times 5 times 1 is 25. That's over 6 times 6 times 6 is 216. And 5 times 5 times 5 is 125 over 216. And if I add them together, I think I'm getting 150 over 216. Okay, have I thrown anything 4 times? Well, obviously, no, I haven't. All right, so that is my probability distribution. Now, there's a really good way that we can check it. And if we think logically, the sum of the probabilities, so the sum of all my probabilities, must add up to 1. So what I'm going to do is I'm going to just double check on my calculator that when I add 1/6, add 5/36, add 150 over 216, does it come to 1? Yes. All right, so that's my table done.